Students, in the previous lecture, we have seen the origin of the idea of free electrons, and we have learned a few of the definitions to understand the electrical properties of materials. In the current lecture, part 2, we will continue with the definitions, and we'll see the classifications of solids, that is the conductors, insulators, and semiconductors. We'll see a few of the relations between the electrical parameters. Then we'll see about temperature dependence of electrical property, which is an interesting one, and merits of CFET, that is classical free electron theory, and failures of classical free electron theory. So after that, we'll have an introduction to the QFET, that is quantum free electron theory, and finally we will wind up by looking into the assumptions of quantum free electron theory. You are familiar with this figure, wherein you see that as we apply the electric field, the electrons are going to move in the direction opposite to the applied electric field. Okay. Now the velocity that is termed as drift velocity, that's all. So that means the definition is, in the presence of the electric field, the charge carriers, that is electrons, will move with an average velocity known as drift velocity. It is in the direction opposite to the applied field. So now if you take by mechanics, by driving force, if you take Fd, then with the help of electric field, we can define that Fd, or driving force, as E into E. E is the charge of the electron, and capital E is the applied electric field. And in terms of resistive force of electrons, if you define again the force, that is a resistive force, Fr, is equal to m into Vd, that is the drift velocity, by tau. So if you take these two equations as equations 1 and 2, since left hand sides are equal, right hand side also you could equate, and finally you could get the equation for Vd as E into E divided by m into tau. Let us go to the next definition, which is very simple, you already know, very trivial also. It is a electric current. Now what is electric current? Electric current is nothing but the rate of flow of charges, okay, or flow of charges per unit time. So that means it is Q, which is in English letter Q is a charge, and T is a small t is a time. So it is a Q by T, that's all, and the unit is ampere. Let us see another definition for current. Previously we have seen current I is equal to Q by T. Now let us have another definition. Okay, here consider a conductor. This is a conductor, whole conductor, wherein you see that I is a current that is flowing through it, and let A be the cross-sectional area, and charge flows, and let its velocity be, drift velocity be Vd. Okay, then the expression can be written as I is equal to Ne into Vd into E. That's all. So where N is the number of electrons per unit volume, E is the charge of the electron, and Vd is the drift velocity, and A is the cross-sectional area. One more definition. So look at this. All these definitions you already know. That is why I am going a bit fast here, but you have the definition written. You can see always. This is a current density, J. So J is nothing but I by A. I is referring to the current, and it is passing through a cross-sectional area. That's all. So the definition is, it is amount of current per unit cross-sectional area that is across the imaginary plane normal to the direction of the current in a conductor, and its unit is obviously I is ampere and A is area, so it is ampere per meter square. Electric field. Electric field is nothing but the ratio between voltage and the length. So that means it is nothing but the potential difference per unit length. That's all the definition, and trivially the unit is volt per meter. Let us see electrical resistivity denoted as rho. So it is nothing but the resistance offered by a conductor of any dimension. When I say any dimension, that means this is a standard parameter with a standard unit, that is ohm meter, unlike in the ohm. So resistance, resistance changes with the dimension, but this is independent of dimension. So if you take R as the resistance along the conductor, and if length L of the conductor and A is the cross-sectional area, then resistance is directly proportional to L and inversely proportional to A. So then if you just introduce a constant, that is rho, so that rho is nothing but the electrical resistivity. So rho is defined as R into A by L, and the unit is ohm meter. Electrical conductivity, it is nothing but the reciprocal of electrical resistivity. So if rho is the electrical resistivity, then sigma is the electrical conductivity. So sigma is equal to 1 over rho. So by definition from the previous, we could just take a reciprocal. Sigma, that is the electrical conductivity, is equal to L by RA, where L is the length, A is the cross-sectional area of the conductor, and R is the resistance. And unit will be ohm inverse, meter inverse. The parameters that we learned, especially the electrical resistivity and electrical conductivity, based on that we can classify the materials as if the resistance, for example, if I consider the resistivity value, if we have the resistivity value of around 10 to the power minus 8 ohm meter, then we can classify them as good conductors or metals. You could see here copper, silver, aluminum or iron, those are the good conductors. If the resistivity is around 10 to the power minus 6, that is the micrometers, then for a few of the alloys you could see that we could classify them. Again, they are good conductors. So that is 10 to the power minus 6 or minus 8, they are good conductors. But in the case of semiconductors, you could see that the electrical resistivity is of the range 10 to the power 2 to 10 to the power 5 ohm meter. Here you could see that it is 10 to the power minus 6 for good conductors, but in the case of semiconductors it is 10 to the power plus 5 or plus 2. So then they are semiconductor. Typically, these values are typically for silicon and germanium. Now if you consider the insulators, then you could see that its resistivity is very high. So that means it falls around 10 to the power 10 to 10 to the power 14 also. So examples are quartz, glass and Teflon, etc., which form a typical insulators. In the next few slides, let us look into a few relations which also you are familiar with. The first one is J is equal to sigma E, where J is a current density, sigma is a electrical conductivity, and capital E is a electric field. Okay, here also I am just giving the equations. We don't have derivations for you in your syllabus. So conductivity, sigma. Sigma is nothing but Ne square tau by M. So its reciprocal is resistivity, that is rho is equal to M over Ne square tau. You should remember this formula to work out a few problems in the later lectures. Next is mobility, which is represented as mu. We have two equations here. One is Vd by E. Vd is drift velocity and E is electric field. And another equation is mu is equal to E tau by M. E is a charge, tau is a mean collision time, and m is mass of the electron. Next we have equation for the conductivity, that is sigma is equal to n mu. So that means we have a relation here between sigma and mu. N is a charge density and E is a charge, mu is a mobility. Next is for the drift velocity Vd, that is equal to E by Ne sigma. Okay, that is for drift velocity. Here I am just giving totally the equations for sigma, that is conductivity. One is L by L by Ra, and another one is sigma is equal to Ne square tau by m, and another equation is Ne mu. Here I am giving you one table for a broad classifications of conductors, semiconductors, and insulators based on the values of electrical resistivity. So you could see for conductors, if the value is around 10 to the power minus 9 to minus 10 to the power minus 5, then they are conductors. If the value of the electrical resistivity is 10 to the power minus 3 to minus plus 3, then it is semiconductors. Okay, and if the value is 10 to the power plus 5 to plus 17, then or higher also, then it is said to be insulators. So hence the value of resistivity helps us to a greater extent to classify the materials, electrical properties based on the electrical properties as insulators, semiconductors, and conductors. And there are a few examples also given in the table. So we had the collection of electrical definitions which were mainly based on classical free electron theory. Now let us try to understand one more property of the conductor, that is the variation of electrical resistivity with the temperature, okay, or effect of temperature on electrical resistivity. That means any metal or a semiconductor for that matter. Now let us look into the metal. Its electrical resistivity changes with the temperature. So that means something, you have a resistivity at room temperature, it is going to be different at 500 degrees centigrade, or it is going to be different at minus 150 degrees centigrade. Okay, so that is given in this figure. As you could see here in the graph, if I could focus on this part, then you could see it is linearly increasing. So that means as the temperature is increasing, the resistivity is also increasing. Okay, resistivity is also increasing. So that means what we have is the positive slope in the graph. Okay, fine. Now if you go down to a temperature, so that means if you go down in the temperature scale and you are reaching, let us say you are reaching 0 Kelvin, hypothetically 0 Kelvin, then the resistivity is not going to be 0, but it will be with some value which we can denote it as rho I, because I refers to the impurities or imperfections. This is mainly because any material which is at higher temperatures in this range, for example, will be affected by the imperfections as well as the phonons. Phonons refers to the thermal waves or thermal vibrations of the atoms. But as the temperature is decreasing, so this thermal vibration is going to be lesser and lesser, and you have the influence of only the imperfections. That is another important issue here. That means no material is perfect. So imperfections is part and parcel of every material, so in the life also. So that means that is why you are having this, and this has been mainly called as the Mathiasen rule. So that means the total resistivity is nothing but sum of the resistivity due to phonon and impurities, okay, which if you just write in terms of the formula, because we know rho is equal to m divided by ne square tau. So for tau you just replace as tau pf, and for impurity or imperfections you replace that one with the tau I. That's all. Okay. Now in this graph you could see, that is in the second graph you could see that there are some alloys, that is copper nickel alloys with different compositions. You could see that for pure copper you are having the trend which is something similar to here, but observe that the rho I is almost near 0. It is not exactly 0 but near 0. Okay, so otherwise the trend is the same. But as you could see that in the alloys with the nickel, with 2% of nickel, that impurity level is increased because nickel is a tertiary element. And similarly with the 3% of nickel, again the rho I is going to increase. Otherwise the trend is going to be same for all the three alloys. But mainly what you learn from this slide is that as the temperature increases, the resistivity also increases in the metal. With this much properties, whatever we have studied based on classical free electron theory, now let us just look into some of the merits of classical free electron theory. So number one is CFET would satisfactorily explain the Ohm's law, that is nothing but V is equal to Ri. Second advantage is that it can satisfactorily explain both thermal and electrical conductivity. Okay, and the third one is that the theory is used to derive Weidmann-Franz law. Means what is that? Weidmann-Franz law is mainly the ratio between the thermal conductivity and electrical conductivity, that is sigma T over sigma, which is nothing but 3 into T divided by 2 into K by E whole square. Okay, so that means except T, because this value, if you could see, that is the sigma T by sigma, which mainly depends on the temperature. Okay, so we have learned that the resistivity is depending on temperature. That's all you could see here, because other things are constant, because 3 and 2 is a number anyway, and K is a Boltzmann constant, and E is a charge. So all those things are constant. So if you take all those things constant together, and you could define another letter, that is L, which is nothing but the Lorentz number. Okay. Fourth merit is that it can explain, that CFET can satisfactorily explain the optical properties, mainly the high luster in the case of metals and high opacity. See, opacity in the metals. Okay, by looking into the advantages and definitions, which could be satisfactorily explained on the basis of classical free electron theory. That means like all the theories which have both merits and demerits, here also we have the demerits or failures or drawbacks. Okay, and there are many, and in your syllabus there are two disadvantages or drawbacks have been mentioned, which I will be highlighting here. So one is that by classical free electron theory, we have the hypothesis that sigma conductivity is inversely proportional to root of T. T is a temperature. Okay, but in reality it is not. Second one, sigma is equal to Ne square tau by m, which you know. So that means what, E is constant and tau and m is constant there. That here it mainly says that sigma is directly proportional to m, and in many cases it is not again. Okay, and there is, while explaining the heat capacity of the electron gas also, the values are not going to be matching with the experimental value. That is also another thing, but it is not there in your syllabus. Let us look into the first two drawbacks. Before going to the explanation of those two failures, let us again look into the assumptions of classical free electron theory. Okay, so first let us quickly see it. First, it is assumed that electrical potential due to ion cores are uniform. So that means entire material will have the uniform electric potential, and the free electrons which are present in the metals which are available for the conduction. And the third one is attraction between the free electrons and lattice points, and repulsion between the two electrons are considered as insignificant. That means they don't have any influence over the conductivity. Okay, so last point, which is important for us for the explanation, is free electron gas. Free electrons in the metals are considered as gas molecules. Okay, so because of that, the kinetic energy of gases, we have it as 3 kT by 2. So kinetic energy, mechanically we can define it as half mv square. So that is half mATA square, which is we equate it to as 3 by 2 into kT. So take that equation, 3 by 2 into kT is equal to half mv square th. Now get the expression for VTH based on the previous equations. So just rearrange that above equation. Then you get VTH is equal to root of 3 kT by m, and which you could see that VTH is directly proportional to root T. T is a temperature. By definition, for mean collision time, we have tau is equal to lambda over VTH. Okay, so that means here VTH is inversely proportional to tau. These two equations we just name it as or number it as equation 1 and 2. Okay, I'm just writing equation 1 and equation 2 in this slide also for the easy reference. So from equation 1 and 2, you know that left hand sides are equal. So that means I can equate the right hand side, which will take the form as tau is inversely proportional to root of T. Okay, but then electrical conductivity is nothing but sigma is equal to n squared tau by m. So that means this sigma is directly proportional to tau. Okay, so which you mark it as equation number 4. So from this equation 3 and 4, you could just compare so that you could see that sigma is inversely proportional to the root of T. Okay, but by experiments, people were conducting the experiments and they saw that this is not sigma is not inversely proportional to root T, but it is inversely proportional to just T. Okay, so that is the experimental value. So that means there is a difference always. There is a difference between root and without root. You could always check with the numerals. So that is one of the failures. Okay, hence we have from classical free electron theory, sigma is inversely to root 2, but for experiment it is inversely proportional to just T. Okay, so therefore the dependence of electrical conductivity is contrary to the observed relation. So another failure, as I mentioned previously, it is between sigma and n. As you could see that it is directly proportional. So that means what it is? So that means as n increases, that means number of free electrons increases, then you should see that sigma is also going to increase. This is mathematically is going to be true. But physically, let us see, is it true or false? Now you consider N for three metals here, for example, copper, zinc and cadmium. For those, you could see that out of 3, for zinc it is maximum, that is 13.1 into 10 to the power 28 per meter cube. Okay, that is N value. And for copper it is less, that is around 8, that's all. Okay, but if you consider the conductivity, that is sigma, then you see that for copper the value of sigma is more, that is 5.88 into 10 to the power 7 ohm inverse meter inverse. But whereas for zinc it is just 1.09. So that means, what is the conclusion here? It means that although the electron concentration in zinc and cadmium are more than copper, the electrical conductivity of copper is higher than both of them. So hence there are two failures that we explained. So like I commented previously, we have advantages and disadvantages of classical free electron theory. So that means we need to have another theory, and people were coming up with another theory which is known as quantum free electron theory. Okay. Many drawbacks have been overcome by the quantum free electron theory, which is the architect is Arnold Sommerfeld. He basically considered Pauli's exclusion principle. And Pauli's exclusion principle, you know that it is nothing but, he says that no two electrons of the same atom may have all their individual quantum numbers equal. So that means individual quantum numbers will be different. So that means there will be different quantum states. So that means there is a quantization of energy. So that means there is a definite these electrons occupying the definite energy level, or they have discrete energy level. This is known as the quantization of energy. Okay, I'll just skip this slide. Here let us consider helium atom, which is atomic number is 2. Okay, and let us consider the quantum numbers. As you have learned previously in the previous classes, we have 4 quantum numbers. One is principal quantum number, orbital quantum number, azimuthal quantum number, and spin quantum numbers. So for helium, if you have done it already in your previous classes, you could see that N could be 1, L could be 0, and ML could be just 0, and that is the spin could be either plus or minus. Okay, then if you just consider along the column, the equation, no two columns are equal. This column is not equal to this column, is not equal to this column. So that means there is no column that is going to be equal. So that means each column is going to be distinctively different. Similarly, if you consider the L shell, then also you could see that for N, where N will be 2, that is for the entire row, it is going to be the same principal quantum number. And in the case of orbital quantum numbers, you have for 0 and 0 initially, and you could assign it as 1, 1, 1 continuously, and ML similarly. Okay, now finally, what is that we need to see here is that neither of the columns, maybe this is not equal to this, is not equal to this, is not equal to this, or any of the columns, they are not equal to each other. Okay, so the conclusion is no two vertical columns, all the 4 values of quantum numbers are identical. Okay, this means maximum number of 8 electrons can exist in L shell, similarly 18 and 32 in M and N shells respectively. And that means energy levels are quantized. In this one I'm just giving you the energy level diagram for hydrogen atom. Here you could see that for the ground state the energy is minus 13.6 eV, and next, that is the first excited state, it is minus 3.4 eV, second it is minus 1.51 eV. Similarly, you have the energy levels for different energies for different energy levels. So here you have to observe that whatever the numbers that I have written here, maybe for ground state or for the excited states, they are allowed energy values. They are nothing but allowed, okay. They are nothing but allowed energy values. So I'm just writing here. So allowed energy values. So those which are between the numbers, any number here, for example, here you could see that between this, what is a possible number? Maybe here it is minus 3 and here it is minus 1. Maybe here it is minus 2, you could write it. But this value is not possible, or you say that value is forbidden. That means, okay, that value is forbidden. Okay, that value is forbidden. Okay, so this is what you have to learn. So that means we have some allowed values, we have some forbidden values. So that means the final lesson here is that energy of electron is quantized. Quantized refers to they are having some quantity. Okay, quantized, quanta refers to quantity. Okay, so that was the explanation for a single atom, that is for the hydrogen. Okay, now let us consider the solid. So in a solid, let us consider a sodium solid. Okay, in the sodium solid, which is having 11 electronic configuration, so which you could write it as okay, you have the electronic configuration here, 1s2, 2s2, 2p6 and 3s1. So I'm just writing it here. So all those things it is written here. So the electrons which are present in s orbital is going to be having the value in this energy band. Okay, this energy band, because individual atoms in a solid is going to have a distinctive energy values. Listen to that very carefully. Each electrons in a given orbital in different atoms in a solid is going to have different energy values. That is why we are having the band. It is occupied here. Okay, so that means next level is what? 2s. For example, 2s orbital. So there are some electrons in all the entire solid which will be occupying in this energy value. So this is the band that you see here. Okay, so similarly you have the occupation in 2p orbital, you have the occupation in 3s, but you see that in 3s it is half. Why it is half? Because it is 3s1. What is its full capacity? Its full capacity is because it is yes, it is 2. Okay, so it is half. That's why I'm just representing here. But the important thing that you should understand is that it is having a band. This is what the origin of energy bands in the solids. All this, how it came from? It came from the assumption by using Pauli's exclusion principle. Okay, so that means this is the main rule which is governing the quantum free electron theory. So this is what you should remember, Pauli's exclusion principle. So with this introduction to quantum free electron theory, similar to the classical free electron theory, let us consider the assumptions for classical quantum free electron theory. Okay, so there are some assumptions which are similar to the previous one. For example, the first one. So first one is that free electrons move in uniform potential within the metal, obeying quantum laws of quantum mechanics. Okay, so that is the first one. See over here, what is that? The first one is the same, that is uniform potential is the same. Even if you compare back the quantum free electron theory, that assumption is same. But what is the rider? Rider is that it should obey the laws of quantum mechanics. Okay, second one is that is the same, exactly the same. That is attraction between the free electrons and the lattice ions, and repulsion between the two free electrons are ignored, which is same as in the case of classical free electron theory. You can refer back. The third assumption is that the allowed energy levels of an electron bound to a single atom is quantized. This is an important assumption here. That means only I have explained in the previous slide allowed energy values and forbidden. So allowed and forbidden. So what are all allowed? They are bound to a single atom and they are quantized. Okay, so fourth one is that the distribution of electrons in various energy levels is controlled by Pauli's exclusion principle. So that means you can't just keep the electrons in any energy levels as you like, but it should govern the Pauli's exclusion principle. It is governed by Pauli's exclusion principle. Okay, so and then finally you have one more statistics. In physics we have three statistics. Here it is Fermi-Dirac statistics that we are looking into. So in quantum free electron theory, Fermi-Dirac statistics is employed to estimate the probability of free electrons. So that is why these electrons are called fermions also. Okay, so these are 5 assumptions in quantum free electron theory. Since we had Fermi-Dirac statistics, I am just showing you there are 3 types of statistics in the physics that we usually learn. One is Maxwell-Boltzmann statistics, another one is Bose-Einstein statistics, and Fermi-Dirac statistics. In this one you see that first one, gas molecules. So that means in the case of classical free electron theory, it is mostly the MB statistics that we deal with. But in the case of quantum free electron theory, it is the FD statistics that we deal. Hence, those elements which obey the statistics are called fermions, which have half spin also, and it is named after one of the scientists, Enrico Fermi. And we have one more particles, that is bosons, which have spin 0 or 1. The name is this is based on the Indian scientist Satyendranath Bose. Okay, let us stop at this juncture for the current lecture, and we'll continue in the next one. Till then, learn these assumptions of quantum free electron theory.